Okay, so today we are going to talk about random variables and expectation. So let me just say a little bit about this topic of random variables. So random variables are at the same time a very simple concept, and they're also a very subtle concept. Okay, so what I'll do is I'll start off presenting it to you as a simple concept, and then we'll get into some of the subtleties. Okay, so mostly you should think of it as a simple concept. Okay, but then when you think it through, you realize that maybe you need to know a little bit more about it to really understand it, and that's what we'll get down to. Okay. The other thing I should say is that this is probably that time of semester when you're probably when a few things happen. One is fatigue sets in, I think, and then the other thing is that you also end up having a lot to do in various classes, projects, and so on. Everything piles up. Okay. So let me just say that, this is also the time, unfortunately, that, we are going to get into some of the most, some really interesting parts of this course, and also parts of the course that'll be particularly useful for you in the final. So it all happens all at once. So I can sympathize, of course, but let me do a little more than sympathize. Let me just offer you a word of advice. So, it's just a word of advice is that, the concepts we are going to be covering from here on out, they all have this same, characteristic that there's a simple way to see them, and there's then also, there are many, many more very complicated ways of seeing those same concepts. Let me recommend you think about them in the simple way because it'll make life much easier for you. So what that means is, as long as you stay on top of the subject, you don't fall behind, you'll find it much, much easier for you, right? So you could fall behind, and then it takes you, 3 times as long to work through the subject, or 10 times as long, and it's just not worth it, right? So just let's okay. So all that said, let's try to get back to random variables. Okay, so let's say that. Okay, so let's talk about probably the most basic experiment in probability. The most basic experiment in probability is that you have a coin, and you flip a coin n times, right? And it's a bias coin, so the probability of heads is p. You can think of p as 2/3, let's say. Okay, so probability of tails is 1 minus p, which is 1/3. Okay? And now, of course, we talked about this before, that once you think of an experiment like this, you have a sample space omega, right, which is all possible outcomes of this coin. So if you think of n equal to 3, then you have all possible outcomes: heads, 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 tails, heads, tails, heads, tails, heads, heads, head, tail, 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 head, tail, tails, tails, heads, and tails, tails, tails. So you have all 8 outcomes, right? But this 8 becomes a very large number as you let n grow. So the sample space is enormous, right? So for even small values of n, a few hundred, n becomes, the sample space becomes enormous. But then what we are interested in usually is we perform this experiment, and then we are interested in some observation we make about the sample. So we are not interested in the actual sample that we got, right? So we flipped the coins, and we got this particular sample. But we are not interested in what that particular sample is. What we are interested in is some synopsis of that sample, right? So we make an observation about that sample, and that might be how many heads are there, right? So now what we want to do is what we are actually interested in is something like number of heads. So now you could ask the question, well, if I flip a coin n times, how many heads do I get? And the answer is, it depends, right? It depends upon what the outcome was. Okay? So this number of heads, so suppose we call this variable s. This is a random variable because the actual value of this variable depends upon the outcome. Sometimes it's 0, sometimes it's 1, sometimes it's 2, sometimes it's 3. Okay? So now you could ask, what's the probability s equal to 0? What's the probability s equal to 1? What's the probability s equal to 2 or s equal to 3? In this particular case, where we flipped a coin 3 times, right? And we'll get an answer for each one. Okay? So this is our random variable s. And then we can ask questions like, what's the probability it takes on each different value? Okay? Okay, does that make sense? It's completely natural, right? There's nothing unnatural about it. It's very simple. Okay, so what's the case out here? So what's the probability of this sample point? It's 2/3, times 2/3 times 2/3. So this sample point has probability 2/3 cubed. What's the probability of this sample point? 2/3 times 2/3 times 1/3. Right, so it's 2/3 whole squared times 1/3. What about this one? It's the same. This one, the same. Right? What about this one? 2/3 times 1/3 squared. What about this one? It's same, right? 1/3, 2/3, 1/3, 1/3, 1/3, 2/3. So it's all the same. 2/3 times 1/3 squared. And this one is 1/3 cubed. Okay. So now you can read them off, right? What's the probability s equal to 0? Well, s equal to 0 happens when? So let me write it like this. When does s equal to 0 happen? S equal to 0 corresponds to all tails, right? This is the only way it happens. So that's s equal to 0. Right? So this probability is equal to 1/3 cubed. What about s equal to 1? When does that happen? Exactly 1 heads. Well, here, here, and here. Right? Is this clear? So this is s equal to 1. Now what's the probability s equal to 1? Well, it's probability of this plus this plus this. So it's 3 times that. (2/3) into 1/3 squared. What's the probability s equal to 2? Well, s equal to 2 is these 3 sample points, right? So it's this. So it's 3 times 2/3 squared times 1/3. What's the probability s equal to 3? It's this one, right? So it's 2/3 cubed. Okay, is it clear? Okay. So now let's do the same thing for a general coin. So say probability of heads equal to p. And now we flip the coin n times. Right? N flips. So now what are the possible values of s? S is the number of heads. Right? So it's 0 or 1 or 2 all the way up to n. So now we could look at what's the probability s equal to k. where there are exactly k heads. Okay. Well, what can we say now about, so now omega, our sample space, is really large, right? It has all heads up here, all tails down here, and then you have exactly 1 heads, 2 heads, 3 heads, right? So if you have exactly k heads, how many such sample points are there going to be in here? So you have n, you have n flips, right? And out of these n flips, we are saying we have exactly k heads and n minus k tails, right? So you want exactly k of these positions to be heads. So out of the n positions, we are picking out k to place heads in, and the n minus k we are placing tails in. So how many ways are there of doing this? N choose k, right? The number of ways of picking this subset. So there are n choose k many sample points. And then once we place the heads and tails, what's the probability of that sample point? The probability we got exactly this outcome where the heads were here, here, and here, and everything else was tails, is what? Well, it's p times p times p for the heads, 1 minus p times 1 minus p times 1 minus p for the tails. So they're exactly k heads, so it's p times p times p, k times 1 minus p times 1 minus p, n minus k times. So it's that much, right? Okay. Okay. So this is called the binomial distribution. Number of heads when you flip a coin n times. Okay? The reason it's called the binomial distribution is if you look at the summation over the probability s equal to k going from 0 to n, well, s is the number of heads when you flip the coin n times. So you know that the number of heads is either 0 or 1 or 2 up to n, right? So if you add up these probabilities, you should get 1. Right? This should be equal to 1 because these are the only possibilities, k equal to 0, k equal to 1, so on up to n. So now substitute probability s equal to k is what? So it's summation k equal to 0 to n of n choose k, p to the k, 1 minus p to the n minus k. This is equal to 1. Right, do you remember this? Is this what the binomial theorem says? No, not quite. I always forget. So what does the binomial theorem say? Maybe it's x plus y, right? Or maybe the binomial theorem says a plus b to the n equal to summation over k, n choose k, a to the k, b to the n minus k. Is that what it says? Right? So now let A be P and B be 1 minus P. So let A equal to P and B equal to 1 minus P. So this will say P plus 1 minus P to the N equal to summation over K, N choose K, P to the K, 1 minus P to the N minus K. Right? And p plus 1 minus p is what? This is 1 whole to the power of n, which is 1. Right? Okay. So that's why this is called a binomial distribution. Okay, so let's back up. Let's just back up to where we are. So what we are talking about is, first, what's a random variable, right? So he said, let's look at the most basic process in probability, which is flipping a coin n times. Okay, basic meaning what? Well, basic meaning it's simple. But basic also meaning that it's very important. So if there's one thing you should learn about in probability, it's everything about flipping a coin n times. Okay, so let's go ahead and flip a coin n times, and then we say we are really not interested in the outcomes, because that's too complicated. That's too much information, right? Okay, so usually the number of coin flips we are interested in, these are not actually coins we are flipping. It could be that we are sampling a population, and we are trying to figure out how many of them are going to vote for Democrats, how many for Republicans. So what fraction, So eventually what we are interested in is what fraction, who's going to get elected. We are not interested in exactly who voted for whom. That's what the sample point is, right? What we are interested in is the eventual outcome, how many heads were there. Okay, so that's our random variable. It's much less information than the entire sample point. So now, what happens when we look at the random variable? Okay, so what happens is, here's something interesting that happens. So the things we are interested in are things of the form s equal to 0, s equal to 1, s equal to 2, s equal to 3. So what is s equal to 2? Well, s equal to 2 is a set of sample points, right? S equal to 2 says there were exactly 2 heads. Now, if you're flipping a coin 3 times, s equal to 2 is the sample point head, head, tails, or head, tail, head, or tails, head, head. So s equal to 2 is actually a subset of the sample space. It's an event, right? So we can talk about its probability. What's the probability s equal to 2? We look up, well, those 3 sample points have their probabilities, we add them up. They happen to have the same probabilities. So we just take 3 times the probability of any one, and we got that number, right? So now, what we are saying to ourselves is, this is the probability distribution, right? If we want to know what's the distribution on the number of heads, this is what it is. The probability that the number of heads is 0 is this number, it's 1 is that number, and so on. So now we know everything we want to know about the number of heads. Okay, and we can do that in general when we have n flips, and we want to know what's the probability s equal to k, and we can compute this probability for every k, and check that they add up to 1. Okay. And now we got the first and probably the most important probability, one of the important probability distributions, which is the binomial distribution. Okay, is this clear? Okay, it's important that you understand these notions in the context of an example first, because now when we take away the example and say, what's a random variable? You might not recognize the concept. Okay? But once you have the example in mind, you'll see that it's actually a very simple concept. Right? It's the only natural way to do it. Okay? But sometimes the natural way to do it takes a long time to work out, and in fact, historically, it took a long time for this notion of a random variable to get formalized. So it took smart people a long time to formalize it, and now, of course, we take it as a matter of course. Okay? So in order to understand it, it's natural that it should take you a little bit of time to understand it. And so it's best that you understand it first in the context of a simple example, and then you say, well, but what is it abstractly? What is it more generally? Because once you understand it more generally, you can apply it anywhere that you want to. Okay? Okay, so now I should say that for this same process where you say, how many, you flip a coin n times, there are other random variables you might be interested in. For example, there's another random variable you might be interested in, which is, let's call it, what do I want to do? Maybe I want to. So possibly there's a different random variable you might be interested in, which says, for example, what is the number of consecutive heads that you had? Okay, the number of places in which you number of places in which you had a heads, and followed by another heads. Okay, so 2 heads in a row. How many positions were there such that you got a head in that position, as well as a head in the following position? Okay, so what should we call this random variable? Maybe we call this random variable x. Number of positions with positions I such that ith flip equal to heads and I plus first flip equal to heads. Okay? So that's a random variable. And we could figure out, well, out there, in each of these, for each of the sample points, we can say, what is the value of x? So let's figure it out. What's the value of x here? How many positions are there such that you've got a heads as well as a heads in the next position? There are exactly 2, right? You got it here and here. Right? How about in this one? What's x? You've got a heads here as well as here, so that's 1. And that's it, right? X of x is 1 for this, 2 for this. What's it for this one? 0. This one? 1. 0, 0, 0, 0. Right? So it was 2 here, 1, 1, and then all these were zeros. Right? So what you report depends not only on the sample point, but what quantity you are interested in. Right? So x, this has x equal to 2, this and this have x equal to 1, and then everything else has x equal to 0. Yeah? Okay. You could also introduce another random variable y, which is number of positions I such that ith flip equal to tails and I plus first flip equal to tails. So now, what do you think y is? Well, y is going to be symmetrical, except upside down, right? So y is 2 here, and then what's y here? It's 1, 0, 1, and then it's 0 everywhere else, right? So this is y equal to 2, y equal to 1, y equal to 1, and then everything else is y equal to 0. Okay? Now, these are variables, right? What happens if you add them together? What if you look at x plus y? What do you think x plus y should be? X plus y should be, well, it's this number plus this number, right? Which means what? It's the number of positions I such that either the ith and the I plus first flip are both heads, or the ith and the I plus first flip are both tails. So it's equal to the number of positions I such that ith and I plus first flips are the same. Okay? And what's that random variable here? So here it is 2. Why is it 2? Well, because x was 0, x was 2, y was 0. Right? So it's 2. What's the other reason? Well, number of positions where the 2 are the same. It's this and this, right? What's it here? It's 1, because x is 1, y is 0. Here, 0, because both are 0. 1, 1, because y is 1 and x is 0. Right? You see how it goes. Right? So once you have this language of random variables, you can talk about adding them or doing what you want with them. Right? You can multiply them and so on. Okay, so now let's go back and think about what is a random variable. Okay. Actually, let's do that after either some questions or a 1-minute break. It's your choice. Yes.
So show it that if that x and y should be independent to add them, or
do x and y need to be independent to add them? See, right now we don't even have a notion of independence yet. Of course, we'll get to the notion of independence in a little while. But for now, x and y are any random variables. But to add them, okay, so we had to have something happen in order to add them implicitly. You know, it was clear from what I was saying that this was true, but you've got to make sure that it's true, which is x and y are random variables which talk about the same sample space, right? You're doing the same experiment, and then, you know, so you think about it this way: you're doing an experiment, and now you look at the outcome, you look at the sample point, and now there are two different measurements you're doing on the outcome. One is x. So x is some dial that, you know, some needle that goes, you know, okay, x equal to 2 here, right? It's counting, or, you know, it's a number of heads in a row. Okay, so somehow you have a measurement device that counts that. There's another measurement device which tells you how many tails in a row there are. And then x plus y is something, you know, you hook both of these measurement devices up to an adder, and that tells you what the sum is, right? So now x plus y is something that, you know, you do this experiment, you get a sample point, and then you look up and you see what's x plus y. Okay, x plus y is another random variable which takes on many different possible values. It's a random value, and it's a random value which depends upon what particular sample point you chose. Okay? Does this make sense? Okay, so let me sort of assure you about one of two things depending upon where you're at. If you think this is simple, let me assure you it's very subtle. If you think it's too subtle, let me assure you it's very simple. Okay? So you know, just make sure you get both parts of the story. Yeah? Okay, so I said you could have a question or a break, and I'm not sure whether I meant it logically or in the English language, but let's just have both then, shall we? Yeah. Yeah. I'm sorry? What's x minus y? Yeah, x minus y is also a random variable. Yeah, but it's an integer random variable. You could have negative value. No, you could just have, you're just mapping it to the integers, right? Yeah. Okay. Okay, so are you ready to, we'll talk now about what is a random variable as a formal object, right? And hopefully when you see this definition, you'll just say, oh, yeah, of course, that's what we were talking about all along. But there's a possibility that, that you look at that definition and you're shocked, because that doesn't look at all like what you thought a random variable was. But then if you're shocked, then go back and think about the example and see that it's exactly what we were talking about in the example. Okay, so what's a random variable? So a random variable x on a sample space. Omega is a function x which maps omega to some numbers. We can take the numbers to be integers or the reals. Let's make it most general. Let's say it's the reals. Okay. Okay, wait. It was supposed to be a variable. When did it become a function? Well, remember what we were doing here? We were saying S is the number of heads. It's random. What does it depend upon? It depends upon the sample point, omega. Right? So S is really S of omega. Right? It depends upon which sample point. So if I got this sample point, S was 3. This sample point, one of these sample points, S was 2, S is 1, S is 0. It's a function of the sample point. Right? It's a random variable. It takes on one of many values. Which value does it take? It depends upon which sample point came up. So S is a function of omega, the sample point. Okay, is that clear? Okay. Now, just for generality, I said it maps to the reals. Actually, what we'll be interested in is discrete random variables. Okay, discrete random variables. Which means what? Which means usually we'll let it map to the integers. Sometimes, for convenience, it might be that we want to map to integers and half integers. That's also okay. So usually what we'll be mapping to is a discrete subset of the real numbers. A countable subset of the real numbers. Okay? Okay, that's a random variable. Okay? Is it clear? Is anybody terribly troubled at this point? Does anybody suspect they'll be troubled later? Yes. You suspect that, yeah. Does anybody want to ask a question now rather than wake up with a nightmare tonight? Yes. I'm sorry? Yeah. S is a function, so S is a function of omega, but omega takes on multiple values, right? So when omega is this, S is 3. When omega is any of these, S is 2. and so on.
Okay, so we're not.
S is a random variable, right? It's
Omega in this case
is the sample space. Omega is a sample. Little omega is a sample point. Capital Omega is the entire sample space, which contains all the sample points. Yeah? Okay. Yes. What would the graph? You mean what's the probability distribution? Okay. What's the probability distribution? Well, you could write out the probability. You know, we have the probabilities of s equal to 0, 1, 2, 3, right? And now you could do a little bar graph, and you could say, well, here's 0, 1, 2, 3. Now, what's the probability of each one? Well, this one is 1/3 cube. Maybe that's a small little line. This is 3 times 2/3 times 1/3 squared. Maybe that's a little bit bigger. And this one probably is a lot bigger. Okay? And 2/3 cube, maybe that's somewhere intermediate. I'm not sure. I'm just guessing, okay? So maybe that's what the probability distribution looks like. So now we've said, what's the probability? It's 0. What's probability is 1? Probability is 2. Okay, so if this is x, this is probability, this is k, this is probability s equal to k. Right? And then we are saying this plus this plus this plus this equal to 1 because the probabilities have to add up to 1. Yeah? Is that what you had in mind? Yeah? Okay. How does S of omega and this thing relate to each other? Okay. So now, that's a very good question. So let me answer that here. Okay. So now, once you define your random variable x, what you're interested in is what's the probability x equal to a? Right? What's the probability x equal to a? So now, let's go back and understand this. Right? So we have our sample space omega. This is omega. We are mapping this to, let's say, the integers. So we have x, which maps this to the integers, to the set of all integers. Okay, so you have 0, 1, 2, -1, -2, ... Okay? And so now we ask ourselves, what's the probability x equal to 2? Well, in order to figure out what does it mean, what's the probability x equal to 2? Well, we look at every sample point omega which maps to 2 under x. Right? X maps each sample point to one of the integers. Right? So look at everything that gets mapped to 2. Okay? So this is all omega such that x of omega equal to 2. Right? All those sample points which get mapped to 2 under this random variable x. Right? This is a subset of the sample space. A subset of the sample space is an event. Okay? So x equal to a is what? It's shorthand for. It's equal to the set of all omega such that x of omega equal to a. Right? This is our shorthand. When we say the random variable takes on value a, what do we mean? Well, we mean what are all the possible outcomes under which, so we do our experiment, what are all possible outcomes under which we actually report the outcome x equal to a? So this is all these sample points, right? So that was here. If we wanted the number of heads equal to 2, what are all possible outcomes under which we report the number of heads equal to 2? Well, it's heads, heads, tails, heads, tails, heads, tails, heads, heads. Right? It's a subset of the sample space. It's an event. Okay? So when we say x equal to a, what do we mean? Well, x is now what? X is a function of the sample point. So we mean x of omega equal to a. Okay? And now what we are saying is, what are all those omegas such that x of omega equal to a? And let's look at the total probability of all of these omega together. That's the probability x equal to a. Right? So it's sum over all omega such that x of omega equal to a of probability of omega. Okay, does that make sense? How many of you feel that the last 10 minutes, the last 5-10 minutes made you forget what you knew about random variables? See, I promised you it was easy, and then it gets subtle, and then you go back and you say, oh, it's easy, what was I, right? So, you're going back and forth between these two descriptions, right? I mean, this is really the intuitive way to look at it. This is what's really happening. But then, if you want to make sense of it, this is the only way to make sense of it. Right? That's the formalism behind it. Right? But then, you look at the formalism and your head spins, so you come back and you say, well, but what's really going on? Well, this is really all that's going on. Right? And now you actually say, well, maybe the head doesn't spin quite as much because, well, a random variable was a map from the sample space to the reals or to the integers. Well, that's what it is here, right? So you have a sample space, and now we are saying we are mapping this to 3, these to 2, these to 1, these to 0. So it's a mapping, right? And then we said, what's the probability that s equal to 2? Well, s equal to 2 is a set of sample points, right? We can identify it with this event, and we can say, what's the probability of this event? It's the probability of this, plus which was that, right? So that's what we wrote down here. It's exactly the same thing. Okay? Okay, so anytime your eyes glaze over when you're looking at this, look at an example instead. Well, the other thing you can do is let them glaze over completely and take a nap and then come back and look at the example. Okay, so is everyone, what do you think? Are you ready to go on with this? Yeah? Okay. Okay, so here's another interesting random variable. It's the waiting time, W, which is the waiting time for the first heads. Okay? So you flip a coin, you keep flipping it until you get the first heads. So sometimes W is going to be 1. Sometimes it's 2, sometimes it's 3, right? It depends upon your luck, how long you have to wait. So if the probability of heads equal to P, what's the probability W equal to 1? What's the probability you have to just wait for one flip before you get a heads? P. Okay, good. Right, the first, W equal to 1 just says you flip the coin and it turns out to be heads. What's the probability W equal to 2? Times P. Right? Because for W equal to 2, it means you flip the coin twice, it was tails first, and then heads. Right? What's the probability W equal to 3? The only way that can happen is you've got a tails, heads, right? That's the only way it could be 3. So what's the probability of that? It's 1 minus P times 1 minus P times P. what's the probability W equal to K? One minus P to the K minus 1 times P. Okay. Okay. So now, okay, remember the reason we looked at random variables is because the samples that we got in our sample space was too much information. Right? And that's the thing you always battle in probability or statistics is too much information. How do you deal with it? Okay, so first thing we dealt with was we introduced random variables so that we focused our mind on the important information. But even after we focus on that important information, we have too much information. Okay, so now what we want to do is focus in on, okay, so we have too much information. Why? Because now we have the probability that S equal to 0, S equal to 1, S equal to 2, and so on. If n is large, that's a lot of information. So how do we actually comprehend all that? We're given this big bar chart, and we look at it, and it's too much information. Or it might be, not only is it too much information, sometimes it's very hard to compute that information, very hard to actually find that information, because it might be too much information to digest and understand, or it might be too much information to actually figure out, to compute. So one way to deal with that is we look at certain statistics about the random variable. And the most important statistic is its expectation. Or average. Okay? So the expected value of x is by definition the sum over all A of A times the probability x equal to A. So for example, for the binomial distribution, the expected value of S is what? It's summation k equal to 0 to n of k times the probability S equal to k. Okay, what is this? This is summation k equal to 0 to n of k times the probability S equal to k was n choose k times p to the k 1 minus p to the n minus k. What do you think? Do you think we can figure this out? We can, right? How would you figure it out? Okay, so there are two ways to figure it out. One is we are going to use what's called linearity of expectations, okay, which we'll see in a little while. Okay? We'll write S as a sum of random variables. Just like we wrote x plus y here, right? We can write S itself as a sum of different random variables. And then we can easily compute the expectation of S by computing the expectations of those random variables. Okay? That's one way of doing it. Okay, that way of doing it is a little bit like this. Okay, so sometimes, often you're tempted to do things like this. So you're trying to compute 64 divided by 16. And then what you do is you cancel the 6's and you get 4. And it happens to be the right answer. Okay? So what we'll do is we'll do this kind of calculation and we'll show that this expectation is what we think it is, which is n times p. Okay, so we'll do that by this trick called the linearity of expectations, which is something like this. It shouldn't work, but it does. Okay? So that's the one way we can do it. The other way we can do it is, actually, it seems like there's something we can do here to simplify it and write it as a binomial and pull it out, right? So remember, k equal to 0 gives us 0, right? So we may as well write this as summation k equal to 1 to n, because k equal to 0 gives us 0, right? And now we write out n choose k as n factorial, k factorial, n minus k factorial. Yeah. And then you see this is very nice, right? Because there's a k and a k factorial. So when you have k factorial, it's just k times k minus 1 factorial. So you can sort of cancel that, and you cancel that and replace that by k minus 1 factorial. Right? And so now what should we do? Shouldn't we just have k minus 1 going from 0 to n minus 1? Okay, we should pull an n out here. Okay, so let's take this n factorial and just pull the n out, and now we replace this by n minus 1 factorial. Okay, and now this is n minus 1, choose k minus 1. Right? Is everyone okay with what I've been doing? I've just been massaging this until it gets to n minus 1, choose k minus 1. So we just get, and now k minus 1 goes from 0 to n, so we get n times, let me call it k prime if you want. Summation k prime goes from 0 to n minus 1 of n minus 1 choose k prime. And let me also pull a p out. So this becomes k minus 1. So I have n times p. And now this becomes p to the power of k prime, 1 minus p to the power of n minus 1. Minus k prime. Okay, and here you have the binomial theorem, right? This is equal to what I have in the parenthesis, in the summation here is 1. Right? Because I'm just k prime equal to 0 to n minus 1 of the probability of getting exactly k prime 1 heads. So this is 1, so you just get n times p. Is this clear? Yeah. Why is this equal to 1? Because of this. Right? This is exactly that with k prime instead of k. Okay. Was that everyone happy with that? Shall we do another one? Okay, let's do another one. So, how many of you would feel relieved if I erase that board? Shall I, or do you want to keep it around? Maybe I should keep it around, shouldn't I? Okay, let me move here. Okay, so let's see, what's the expected value of W? So the expected number of steps that you have to wait till you see the first heads. Okay? What would you expect it to be? So if the probability of heads is P, so if the probability of heads is 1/2, how many coin flips do you expect to make before you get a heads? Okay, let's figure it out. let's write it out. It's sum k equal to 1 to what? Infinity, right? Of k times probability w equal to k. Okay, so it's summation k equal to 1 to infinity of k times 1 minus p to the k minus 1 times p. Now this looks utterly horrible, right? It looks impossible to do. Well, okay, we could pull this p out because obviously it doesn't depend upon k, but how do you ever compute such a sum? Okay, so there are two ways of doing it. One is you compute it, the other way is you do something tricky. Okay, unfortunately in this case, even to compute the sum you have to do something tricky. So we'll do something tricky either way. Okay, so the way we compute the sum is we say this is p times summation k equal to 1 to infinity of okay, we just let k be a formal variable and look at this as a derivative with respect to k. Okay. I mean, it's a trick, don't ask me, I didn't invent this. Okay. And then
Should it be
1 minus p. Is it 1 minus p to the k? Let's just write it as q. Should we write it as q? Wouldn't that be much easier for us? Let's make it q. So q is 1 minus p. Okay? And now we can pull the derivative outside the sum. So it's p times summation over k equal to 1 to infinity. No. P times d by dk of summation of q to the k. So we can pull out p times q times d by dk of summation k equal to 0 to infinity of q to the k. So it's 1 plus q squared and so on. So when you sum up this geometric series, it's 1 plus q squared plus so on up to infinity. You know that this is 1 over 1 minus q. Right? So you get p times q times d by dk. What am I doing? It's not d by dk, d by dq, right? So derivative with respect to q of q to the k is k times q to the k minus 1. Okay? So what's the... Okay, so this summation is 1 over 1 minus q. And if you take the derivative with respect to q, you get what? It's 1 minus q to the minus 1, so you get derivative with respect to q is minus 1 times 1 minus 1 over minus 1 over 1 minus q squared times minus 1, is it? Do we get another minus 1? Is that correct? So we get plus. I seem to have made a mess of it. Did I have to pull out a q? Sorry, let me see if I have. So I've obviously done a. Oh, sorry, Oh, sorry. Yeah. I'm sorry. So, okay. So let me just go ahead. Okay. So let me just go ahead and do it right, because if I try to fix it within what I did, it would never be it's too complex. So should I just start here? So what we were doing was P times K times Q to the K minus 1. Now what we did was we said K times Q to the K minus 1 is d by dq of Q to the K, right? Okay. And now what I want to do is I want to take the derivative outside. So it's P times summation K equal to 1 to infinity P times d by dq of summation K equal to 1 to infinity of Q to the K. Okay, now, of course, I can't pull the Q outside the d by dq, right? That would be wrong of me, right? But I can pull it outside the summation. And so now I get, which is what that's what I was doing earlier, which is completely wrong. I can't pull the Q out of the d by dq, but I can pull it out of the summation. So I get P times d by dq of summation of, now I can pull the Q out, so Q times summation K equal to 0 to infinity of Q to the K, right? So I pulled one of the Q's out, and now I can go from 0 to infinity instead of 1 to infinity. Okay, now this summation I know how to do. That's the geometric series, starting with 1 plus Q squared. That's 1 over 1 minus Q. So this is P times d by dq of Q divided by 1 minus Q. How did I get that? There was a Q here, and then this summation is 1 over 1 minus Q. Okay? Okay, now this thing is what? Well, if I write it as P times d by dq of Q minus 1 over 1 minus Q, so I can write this as Q minus 1 plus 1, and Q minus 1 over 1 minus Q is just minus 1, so d by dq of that is 0, and then 1 over 1 minus Q, right? So this is P times the derivative of 1 over 1 minus Q with respect to Q. And what is that? It's basically 1 over 1 minus Q whole squared. Okay, but Q was 1 minus P, so this is P divided by P squared, which is 1 over P. Okay, so that's the short answer. The expected value of W is 1 over P. So the probability of heads is P, and the probability of the expected waiting time is 1 over P. Okay. Now, this makes sense, right? The smaller the probability of heads is, the longer you have to wait for heads. Right? Okay, I told you that, yeah.
So why do you upper bound K to the infinity instead of
I'm sorry?
Why do you upper bound?
Because now the experiment is different. We are not going to stop until we get the first heads. And we don't know how long we have to wait till we get the first heads. Right? there's a small chance that even if we toss it 1,000 times, we won't get a heads. So we have to keep going up to as long as we need to. Of course, the chance drops off very, very quickly. So if you want to stop at 1,000, you'll get basically the same distribution, but it'll be off slightly in the tail. Okay, so I told you there were, in order to compute the expected value of W, you have to do something tricky. There's another tricky way you can do it. What you can do is you can say, well, what's the expected value of W with probability P? It's 1, right? With probability P, you get a heads right away. So the waiting time was 1. Plus, with probability 1 minus P, how long do you have to wait? Well, the first flip was useless, so you got a tails. And now how long do you have to wait after that? Well, it's like you're starting from scratch, right? If you got a tails in the first flip, now how long do you have to wait? Well, the fact that you already flipped once and you got a tails doesn't change the fact that you have to wait. It doesn't change your waiting time. You still have to wait this. It's as though you're starting from scratch, right? You leave aside the first flip, and now starting with the second one, how long do you have to wait? Well, exactly the expected value of W. Does everyone see that? Because coins don't have memory, right? So the first flip is done. It's over with. You don't care what happened. From then on, if you start watching, how long will it take you till you get the first head? It's exactly as though you're starting from scratch, right? Does everyone follow this? So you're saying, what's the expected time I have to wait till I get the first heads? Well, there are two possibilities. Either I have to wait only one step with probability P. With probability 1 minus P, I already waited one step because that was a tails. So I got a tails here. And now from here on, I'm starting from scratch, and I'm saying, how long do I have to wait? Well, how long do I have to wait? It's the expected value of W. Right? Because the fact that I flipped this doesn't make any difference to the future. Right? Okay, so if you buy this, then you just, so what is this saying? This is P plus 1 minus P, so that's 1 plus 1 minus P times expected value of W. So now you take this to the other side, you get, you subtract 1 minus P from here, so you get P times expected value of W equal to 1, so expected value of W equal to 1 over P. Okay? Is everyone clear? Yeah.
So is that definition kind of like wavy rule? Is it kind of a restricted?
It's sort of conditional, so you're saying, well, the expectation is, well, P times, with probability P, this you have this much expectation, and then with 1 minus P, you have, okay? Okay. How is everyone doing on stamina? Are we stretching things a bit? Let's maybe a question or a 1 minute break. Yeah. In which one? Yeah. Oh, okay. So I said P times 1. So you get P plus 1 minus P plus 1 minus P times expected value of W. So P plus 1 minus P is 1. And then expected value of W minus 1 minus P times expected value of W is P times expected value of W. So I just moved this across to this side, and I added these two together. So I got P times expected value of W equal to 1. More questions? Should we take a 30-second break? Okay, so let's just, okay, so what I'll do in the last few minutes is I'll just tell you a little bit about linearity of expectations. Okay, so remember way long ago we talked about how you can have, random variables x and y, and then on the same sample space, and then we can talk about x plus y, right? So x was, where was x? There's where it was, right? So x was, do you have the same the same, was the ith flip equal to the I plus first flip? What were the number of positions I such that ith flip equal to I plus first flip equal to heads? Y is number of positions where they are both tails, and x plus y then becomes what's the number of positions where they are both equal. So now you could compute the expected value of x, you could compute the expected value of y. Now if you want to know what's the expected value of x plus y, it's always equal to the expected value of x plus the expected value of y. Okay? This holds, if you have a sum of random variables and you look at the expected value, it's the sum of the expected values. For example, S equal to number of heads in n flips. Okay. So now let's write down some more random variables, right? Because so what we could write down is x sub 1 equal to 1 if first flip is a heads, and 0 if tails. Right? Similarly, we could write x sub 2 equal to 1 if second flip is a heads, 0 if it's a tails. In fact, let's write x sub I equal to 1 if ith flip is a heads, and 0 if it's a tails. Okay? So now we can ask, what is S in terms of the x sub i's? Well, first, before we do that, let's figure out what's the expected value of x sub I. It's just 1 if it's a heads, 0 if it's a tails. Right? So what's the expected value? It's 1 times probability of heads plus 0 times probability of tails. Right? Which is 1 times p plus 0 times 1 minus p, which is just p. Right? The expected value of x sub I is p. Right? If you toss a coin and you say 1 if it's heads, 0 if it's tails, the expected value of that random variable is p. But now, you can also write S in terms of the x sub i's. S says how many heads are there. X1 says was the first flipper heads. X2 says was the second flipper heads. So what's S in terms of the x sub i's? X1 plus X2 plus X sub n, right? Because this tells us whether this was a heads or not, heads or not, heads or not, so on, right? So this is just counting how many heads do we have. Okay? But now use linearity of expectations. So the expectation of S equal to expectation of this. Now use linearity. So it's expected value of x1 plus expected value of x2 plus expected value of xm. Well, what's the expected value of x sub I? It's p. So you get n times p. Right? And that was this whole calculation out here. Right? Okay. So how hard do you think it is to prove that expected value of x plus y is expected value of x plus expected value of y? I'm sorry? It's okay. It's not bad, right? Okay. So let me, I have just 2 minutes, so I'll just give you the main idea behind this proof that expected value of x plus y equal to expected value of x plus expected value of y. So say that you have a you have this, you have these numbers in here. Okay, and I'll put in arbitrary numbers. Of course, these numbers are going to be probabilities, or expected. Okay, so I'll just put in numbers, some numbers here. So this was 2, 5, 0, 1, minus 1, 3, 8. I'd better not use large numbers because I have to add them up. Okay. So now I'm going to do two things. One is I'm going to add up the columns. So I add up this column 2 plus 0 plus, okay, this is 10, right? The column, sum. And this column adds up to 15. Is that correct? Yeah, okay. Now, and then I add up these two to give me 25. Okay, that's what I get if I add up the two columns. The other way I'm going to do it is I'm going to add up the rows. So I'll get 7, 1, 2, 10, 5. And now what happens if I add these up? What do you think I'd get? Well, I'd get 10 plus 20, 25. I get the same number, right? Okay. Is it a surprise that I get the same number? Well, it's exactly as surprising as the fact that expected value of x plus y equal to expected value of x plus expected value of y. Okay? So I claim that there's something. Okay, by the way, this is really exactly what the proof of that statement is. I'm not just making an analogy. This is exactly what it is. Okay? This would, here would be omega, this would be the sample space omega, so you have omega is down here. This is your random variable x, this is y, and now you're adding up. This is x plus y. Okay, so when you add down this way, you're computing expected value of x, you're computing expected value of y, you're adding them. Here you're taking x plus y and you're computing its expected value. So that's what it corresponds to. Okay, so I'm doing it too fast. You're not expected to understand this, but this is really what's going on. Now the point is, the reason you get the same thing is because you're just adding up all the numbers inside this matrix. And the point is that when you actually use it, it simplifies calculations, and you get results which you would never expect. So how hard is it to believe this? Well, it's as hard as the results we use it for, which is, it's really a piece of magic. Okay? All right.